Some people. All right, so now we're talking about cluster evaluation. Cluster evaluation is basically producing metrics that will tell you that aims at quantifying the goodness or the quality of your clustering. So there are two main categories of measures. So there are external measures and there are internal measures. You'll see external measures primarily like that's all supervised learning. It's like, at least for neural networks, it'll be all like supervised learning. This is when you have a data set of observations and you also know what the expected outcome should be no matter like for each of those observations. Internal measures are like deriving goodness from the data itself. This is when you don't have the external ground truth. And so unsupervised learning tends to take advantage of these types of measures. Cool, so we'll go into external measures. Cool, so there's a lot of words here, but basically like all this is saying is that there is a data set of n points, right? And they will be partitioned into k clusters. And the ground truth is the same length as d, and you'll have also k given clusters or ground truth clusters. And so we call this this data set of t, I guess tau, as the ground truth partitioning. Think of it as the same thing as creating clusters. Your set of yi clusters, those are your predictions. And then ground truth also creates its own version of clusters, and then you're mapping them together. But I'll keep explaining. I didn't do that great of a job of explaining, but this will show you a little bit. This will explain a little bit better. So we talk about purity as the extent of, it quantifies the extent that cluster CI contains points only from one ground truth partition. So if you look at the math here, what it's doing is the purity of I is 1 over Ni, and then the max of N of I of J. So I'm going to take for this example, let's look at T3. T3 is in black, it's circled in black, and then the black data points are all in cluster 3. So if you look at this, like this example follows that. So the ground truth is circled in black, and there are a total of 9 data points in the ground truth labeling. This is the ground truth is basically like, okay, this is the correct thing. And my clusters are my predictions. So I'm predicting that I've predicted that there are 7 of my data points out of the 9 that should have been labeled the same as, that should have been labeled black so there are 7 out of 9. Do you see how that's happening?
Wait, don't you have that flipped? Isn't ground truth colored black?
No.
No, because if you see like all of the ground truths are filled in, and then clusters are outlined.
Yes.
Yeah. So what I'm saying is that your ground truth are filled in as black. So there are only 7. There are 7 data points that are truthfully.
You said it the opposite way before.
I did say it the opposite way. Yeah. Okay. So there are 7 data points that are truthfully black, but my clustering algorithm has included 2 extraneous data points that should not fit in my cluster.
Yes.
The ground truth would not have accepted. So the purity score is 1 over N3, which is basically, it's 1 over 9, which is 1 over the total number of data points that fell into your cluster C. And then you're taking the max of N of 3.1, N of 3.2, and N of 3.3, which is the number of data points that were correctly scored in each of the clusters, right? So in my first cluster, in C of 3, N of 3.3 is the black cluster, and you see that there are 7 out of 9 in that cluster. So I mean the number is 7. There are 7 data points in cluster 3.
Yeah.
In 3.2, which is the orange one, there are 0 black dots in that cluster.
Got it.
And then in N of 3.1, there are 2. Wait.
Oh
Oh,
shit.
I got that. I got that mixed. I got that mixed up. It's all within T3, but it's saying like, okay, my T3 is black. There are 7 black dots. The second value, which is T2, which is blue dots. There
Oh,
are 0 blue dots in my cluster T3. Because it's saying that so n of 3 1, n of 3 is cluster 3, and then 1, which is ground truth label 1,
Mm,
got it.
which is orange. So there are 2 of those.
Hmm.
So your first value is your your first value is your cluster selected, and your second subscript is your ground truth label.
okay.
And so here you're able to calculate the like the purity of your clustering. So we talk a little bit about total purity of clustering C. It's a weighted sum. Um,
Of all the
which,
individual purity?
yeah, so that makes sense, correct?
Yeah.
And so it
So
asks you,
Ni over N means the number of points in cluster I over the total number of points.
yes,
Okay.
Times the purity score. Okay.
times its purity score, right?
So, okay. Where R represents the number of clusters. No.
Uh, the radius of the clusters.
Fuck me.
No,
No,
it's a
you're right.
number. It's a
It is.
number.
It's the number of clusters. Sorry, there is another place
Okay.
where where R represents radius. My mistake.
And N represents the number of points.
Exactly. Yeah.
Okay.
Okay. So what is the purity value for a perfect clustering?
1.
But why is it 1?
Well, because um, you would have that, yeah, all the weightings, all the weighted. Yeah,
Can I?
basically this second equation, or this like second part of the equation, is going to give you n, and then you'll just have n over n, like in the sum.
Yeah. The intuition actually, like behind why a perfect clustering algorithm would have a purity of 1, is that for every T partition group, for every ground truth partition, there would be 1 data point in it. Your ideal purity would be a
Oh,
1-to-1 clustering algorithm. So you would have T number of T partitions, and you would have C clusters C clusters, and they would each map 1-to-1 if you for a purity score of 1.
Right. So if you look at that second equation, that should equal 1,
Hmm.
right? And then
Right.
we do a weighted sum based on the number of clusters in each. So that should sum up to 1 total, right? Of
Exactly. Yeah.
our clusters.
Exactly. Okay. Here's an example, and they have I think these are called confusion matrices.
Hmm.
Uh,
Yep. I'm confused.
and so here you can actually see like they've calculated what purity 1 is, and purity 1 is 30 over 50, right? So let's look at how they got purity 1 to be 30 over 50, right? Um, how did they do this? I did this example. Okay, so to get 30, it looks like T1, you pick the max of your C1, so the max value is T3, and your sum in total was 50, so it's 30 over 50. It's that max algorithm.
mhm.
Uh, Same for purity, you're taking 20 over 25. For C2, you look across the row and you're taking the max value of T1, T2, and T3. For C3, you're again taking the max across this over the sum. And the purity, the weighted sum purity, is the sum of all your purities divided by the total number of data points. Make sense?
Yeah. Wait, can you scroll up one more time?
Up to up here?
Yeah, I want to look at equation, the first equation again. I'm
Yeah.
trying to remember why you want the max of the.
Because you want to get so in that cluster that you're looking at.
You want the highest overlap. effectively what that means, overlap between ground truth and then your labeled data points.
But like, let's say that you really fucked up, and you in your cluster you have more from ground truth 2 than you have from ground truth 3, right? So we're looking at the second equation now, and let's say that you have more from ground truth 2 than 3. You're still going to get, a high purity score, even though you actually fucked up. You were circling the wrong one. So like, does it? Maybe the idea is.
I don't think that's true. I think if I'm understanding this correctly, the way Dan explained it is that like n31 is the number of points in cluster 3 that you've created,
Right.
so like your C3, that are in ground truth 1.
Exactly. So so the thing about this algorithm is not so much that.
Okay, so I guess you're right actually. Because if you have more points, yeah, Stuart's right, because if you have more points in this cluster that are red or orange or whatever,
Yeah.
in cluster 3, then this purity would still be just as, like if there were 7 orange ones and only 2 black ones, then this would be the same value.
Right. So
Yeah.
I guess it's arbitrarily, like, we could get the clusters mixed up. This algorithm doesn't care.
Exactly.
Oh, that's really dumb.
Well, okay. So I guess there are downsides to the algorithm itself, like this usage of metric. But you do know that your ground truth labeling is always correct, and your cluster C is your own prediction on how to organize that data. The partitions are always right. It's your clustering, your representation of C that could be wrong.
But what he's saying is that you could,
Yeah, the math, it works out where if you messed up the way that you circled or you partitioned yourself, like you created your own clusters, the purity score could be equally as high. So it's up to you to pick certain metrics. Alternatively, you don't even have to use purity. You could use other metrics we're going to learn about, which is more common now than using purity.
So what I'm thinking
downsides he's
now
talking about is one of the big reasons why people don't use purity scores.
Okay.
But
Yeah.
what I'm thinking now is that will it I think it might still reflect in the total purity, because if you had a heavy skew in one cluster of like the wrong points, then that'll significantly reduce your total purity, right?
Yeah.
Is that true or no?
The weighted sum purity?
Yeah.
Well, yeah, because if you're wrong, if you're specifically wrong in one cluster, that means that there are other misrepresentations that propagate through the other clusters as well, right? Because you have a total net sum of data points. The total sum of data points is still within your set X.
Yeah.
Right. So if you haven't found the optimal the optimal C's, you're gonna see that error propagate.
That makes sense. Yeah. Okay.
Yeah. Okay. So let's keep on moving. We're chugging along. Yeah. So here's the thing: 2 clusters may be matched to the same partition because of that max algorithm. So if you look at C1 and C2 here on the left, the max value of C1 would be 20, so it's pointing to T2. Or actually, no, it's the max is 30, so it's pointing to T3, and then C2, its max value is 20, so it's pointing to T2. And then if you look at the right side, C1 and C2 both pair to ground truth partition T2. And they give you the same purity score, so or the same weighted purity. So this is kind of what Stuart was getting at earlier.
Yeah, I see.
Maximum weight matching, only one cluster can match one partition. So now the algorithm was improved upon so that your max has to correlate to a 1-to-1. But so it's saying that, for example, if C1 is paired to T2, then C2 and C3 cannot be paired with T3 or T2. And so you can see already, you can think about that there will be a problem as a result of this, right? The problem that arises is that you might have something really close. So like in this case, C1 is more paired with T2, or you get a purity, you get a score of 0.6, and then C1 is more paired with T3, 0.65, but the issue is that they're really very close together. So that means that, like, yes, one is like bigger than the other, but there's a lot of variance, I guess. Like your value, like your decision to, like, I don't know, I don't know how to explain this, but you understand, do you see like what I'm saying? Like the problem is that it's almost just as likely to have been paired with T3 than with T2. I mean that backwards.
I think so.
Because you're just using the numerical number, like the numerical output, to determine whether C1 gets paired with T2 or with T3. And if you look at the purity scores, their purity scores are pretty close.
Yes.
It's 0.6 or 0.65, right?
Mm-hmm.
And the higher your purity score is, the more correct your original clustering C is.
Yeah.
So if you have two mappings with really close purity scores, that means that either of them could be predicted, and the one you didn't predict still has a high correlation with the other cluster. Or
Yeah, it
the other
means your
partition.
clustering is shitty.
Yeah, that's what it comes down to.
Okay.
So that's why purity has the issues. Now we're looking at matching-based measures, so maximum matching. This is just the generalized expansion of what we were talking about above. So the drawback of purity is that two clusters may be matched to the same partition. So the correction was that you would have a maximum purity and add a constraint so that you can only match cluster C to a singular T, and that once that connection has happened, the others cannot be matched that same ground truth partition. And so if we look at this example of maximum matching, 0.65 to 0.6 is greater than 0.6, but that still has a really high correlation. So if you look at this is talking about C1 versus like C2, or C1 versus C3. In there could have been a different bubble, a different C, where that actually encompasses the two orange dots that are in the black and the two dots that are in red, and created a new cluster there, but it didn't. Yeah, so I'm not exactly sure why there's a dartboard in the middle of. I don't know what that was about, but it must be about precision, recall, and accuracy. So there's a lot of, I guess, in a lot of machine learning, we look at like precision, recall, and accuracy specifically because you care about your predictions. It's not just about your predictions and your outcomes. It's about your true positives, your true negatives, your false positives, and your false negatives, as a way to determine how good your system is performing. So when you have a correct prediction, and this is again with labeled data with labeled ground truths. You are taking your number of positive labeled data, and if you get a correct prediction, that's true positive. If you have your number of positive, your system labels as positive, but the prediction is wrong, that's a false positive. And then, so like the same for negatives, right? So precision is defined as the true positive divided by the actual results. So that is further expanded as true positive divided by true positive plus true false positive. So you only really care about the positive values. So whenever you're like all things related to your data being labeled positive, whether correctly or incorrectly. So that's precision. Recall is the true positive over the actual result or predicted results. So recall is about like, so this is expanded as the true positive divided by the true positive plus the false negative. So this recall is more about, I guess if you're incorporating false negatives are when your system labels something as negative, but it actually is incorrect. So it should have been positive.
Mm-hmm. So this is your total predicted results.
Yeah, your total predicted results, right? And then accuracy is the true positive plus the true negative divided by the total. So a lot of times we do a lot of accuracy scores tend to come out for, primarily are used in classification systems. So when you work on neural nets that take a picture of a cat and try to tell you if it's a dog or a cat, we use accuracy scores to evaluate our models.
I feel like that's the least useful of the three.
Accuracy?
Yeah. I feel
Well,
like
yeah.
it equates, I don't know.
It honestly, it depends on your use case a lot of the time. Because a lot, like you can apply machine learning to so many different avenues or industries or types of problems even. So it's not, accuracy is fairly useful as a metric for image segmentation. Like if you're doing like any sort of image processing or labeling, that tends to be a very useful score because
I feel like if it's really high, it's useful, right? Because like it's only going to be
it's only going to be high when it works as expected.
Yeah.
In correctly calculating true positives and true negatives. So F measure is the most, okay, so F scores are usually, they're really well, highly used in machine learning for evaluating models. Here we talk about precision. So precision measure quality. Quality is the same thing as purity. So this answers the question, how precisely does each cluster represent our ground truth? So again, we're picking the max of our data and the cluster. So this precision is the same. Precision is the same exact thing as the accuracy. I mean, as the purity. Recall measures completeness. So how completely does each cluster recover the ground truth, right? If you look, like this example does a really, this is a good representation. So if you look at precision for cluster one is the orange. It's 6 out of 6 orange data points. So all of your ground truth, T1, all of the data points belong to the same ground truth partition. So in precision, this would be very high. Your purity is a 1. But in recall, this is taking the total number of data points that fall under the ground truth labeling within your cluster versus the total number of data points within that ground truth partition. So there are 10 orange data points, but only 6 of them fall within cluster 1.
I see.
Can you go back up to the definition of recall real quick?
Yeah.
And just close the loop on that. No, up a little bit more is what I mean, like the original.
Oh, this is the recall, yeah. True positive over predicted results.
True positive, false negative.
So this is true positive plus false negative. So the false negative part is the values of the ground truth data set or the ground truth partition that are not a part of your original cluster selection.
Yeah, I don't know why that says predicted results. That should say the true results, like the truth, right?
Yeah, it should say truth. So, but the really easy way to think about it is look at all the data points that are a part of my ground truth within the cluster I'm picking or looking at over the total amount of data points that fall in that partition.
Mm-hmm. Yeah. Mm-hmm. Okay. Measure of completeness.
Exactly. So it's a measure of completeness.
Okay. So precision is purity.
Mhm.
Got it.
Recall is completeness. How well do I encompass the spread of my data points? Again, here's the math for precision versus the math for recall. So here we are doing, again, the max value for C1 is T3. So that would be 30 over 50. So that's what our precision is. Our precision for C2, it's 20 over 25. And then our precision for C3 is 25 over 25. Now, recall is different. Recall is the, for cluster 1, recall is 30 over 35. So you can
How
see
many did you get right, basically?
exactly how many did I get right for my cluster. So it's pretty, it makes a lot of sense to me. It's pretty straightforward. So now we're looking at if an F measure takes into account both the precision and the recall so that you get a holistic understanding of how good your clustering is. And that's what the F score is. There are different types of F scores. So if we look at an F measure is the harmonic mean of precision and recall. It takes into account precision and completeness. And so if we look at the equation right here, it sums, or it eventually, it's 2 times the precision of I times the recall of I over the sum of the precision and recall. And so if we go down a little bit, we'll look at what the F score or the F measure is for the clustering C as a general formula, which is just 1 over R, the sum of F of I. So F1, the F score for cluster 1, which is 60 over 85. So if we look at cluster 1, which is the orange one, you're writing the calculation for this. So we went and got the recall value, which is 30 over 50, or 30 over 35. The precision was 30 over 50. So you take those values and you come down here and you just plug them in, and it returns you 60 over 85 for F1. That's cluster 1. So this gives you a better understanding of how well does my cluster encompass the homogeneous set of data points from the ground truth partition, as well as how well does the cluster actually contain the total amount of data points, the spread of data points within ground truth 1. So the optimization between the balance between those two things will give you your optimal clustering. Does that make sense?
So you could optimize. Okay, got it.
Right. So it really depends on what you're optimized for, and it usually comes down to the use case. So there are some types of problems where having a false positive or a false negative is too detrimental for the system. So you would never want to use an F score to measure the accuracy or to evaluate your model. Things like a medical diagnosis, right?
Mhm.
A system that does that cannot afford for there to be a false positive or a false negative. It's much more harmful for a false negative because a person would die than a false positive, which causes undue stress for the person.
Yeah, I see.
So an F score cannot take into account, or you could not use an F score for a system like that because it takes into account false positives or doesn't heavily penalize either or, right? Okay, entropy-based measures. So what we're going to look at here for this, you're doing the exact same things that we did in the information theory, where we calculate entropy, calculate cross entropy, or for conditional distributions, where this time we're treating the conditional distribution, or the conditional entropy is just between the clusters we predicted and the truth partitions. And so the calculations are exactly the same. It's the probability of getting cluster I times the log of the probability of cluster I. So calculating the entropy is the same. And here you can see down, they put a little note where the probability of cluster I is the probability of n of I of 1, n of I of 2, to n of I of k. Then you're summing them all up together. So that intuitively means this data point 1, falls into cluster cluster 1, 2, or 3, or however many clusters I have, right? That's
Oh,
how we define this, because I think we said that for the max n of I is the cluster you selected, so it's either 1, 2, or 3, and then the partition. Did I get this backwards?
I think you had to write that where I is the cluster selected,
Mm-hmm.
and then the second one is the ground truth label.
Yes, that's it. And so that'll help you calculate so the total number of data points that are in that cluster, or in that cluster, divided by the total number of data points in that ground truth partition. Or no, the total number of data points in general.
I see. So this is the probability of any data point landing into this cluster.
Exactly. So if I have 10 data points and I have 3 clusters, but 6 of them are in the first one, then I have a 6 out of 10 probability.
Yeah, so you're just sort of considering the entropy for each thing. Like you have clustering, and then you have your ground truth, and you're
you're calculating the entropy of the clustering, which is your predictions, and then your partition T. Conditional entropy is exactly the same thing as what we defined before. It is just the entropy of your ground truth partitions given your clustering. So it's how the ground truth is distributed within each cluster. That's what this entropy is. Oh,
Okay.
and here they actually did label N of I is the cluster C, J is the ground truth T. So entropy-based measures. So here, here's something is a little bit different, right? So they're doing the joint, not the joint. They're doing the conditional entropy of T given clustering C, right? So that results in a double summation where you take the probability I of J, and they've defined what I of J is as N of I of J over N, which is all the data points that fall in both that cluster and that ground truth label over the total number of data points. And then PCI is the number of data points in P of C, or in that cluster, over the total number of data points. So you're looking at how many data points are both in cluster C and ground truth label partition T over all the data points we have. So that's like an average, right? It's a probability. And then you're taking the probability of any data point falling in cluster C over the total number of data points. And this breaks down to basically the joint distribution of the cluster and the ground partition minus the entropy of the clustering, right?
Mm-hmm.
So what they've written in blue is important. So the more cluster members are split into different partitions, the higher the conditional entropy is, right? So what this is saying, is basically like the more and more clusters that the more and more clusters are split into more and more partitions, the higher the conditional entropy is. So that would mean that
No, that's not what we want.
yeah, that's not what you want. You want lower entropy so that you have more information about your clustering. We have the conditional.
But if they're sorry.
No, go for it.
But if they're all in the same cluster, then you have. Okay, that makes sense. Yeah, you have low.
Yeah.
Well, you have low. I understand that you have low entropy for. Yeah. Okay, that makes sense. Yeah, I get it.
Okay. So now we're looking at the conditional entropy of the ground truth partition given C, given your clustering C. It's equal to 0 if and only if tau is completely determined by C, corresponding to the ideal clustering.
Mm-hmm.
So this is that case where this is the case where you have the one-to-one ideal mapping, right?
Mhm.
Got it.
Yeah. So you don't actually have entropy if everything is fully deterministic and actually is, if you have a really specific, it literally falls in line with the idea that if I have 10 data points and I have 10 clusters, that means that I have 10 ground truth labels, um, or I have 10 ground truth labels. So there is a very high specificity to the way my data is ordered. And as a result, there's really, really low entropy. So it's zero entropy, right? It's a very uncommon event. And there's, again, high information as a result of that. This is pretty straightforward too. If the cluster and the ground truth partition are independent of each other, this is just saying that the entropy of C will not, the entropy of C has no effect on the entropy of tau. Again, if there is no probability based, if they're both independent, then the probability of tau uh, will not be affected by the probability of C. So as a result, there's no way for the entropy of C to affect the entropy of tau. Does that make sense?
Mhm.
Okay, I think we're almost done. It's just some derivations. Yeah, I don't really
Yeah, you can
have
save
much to
it.
say about this, but
Yeah.
That's fine.
you see with the math. And so they've done again that same kind of graphic here. You have the total entropy of x and y. You've got the entropy of x, and then the entropy of y given x, and how they're symmetric. So we have mutual information. There is mutual information to be gained between the clustering itself and the ground truth partitions. So that is, again, P of I of j, which is the probability of cluster I being in ground partition j. Uh, and we defined what that is above, so you can go back up and see that it's n of I of j over n.
Mhm.
And then you have the log of P of I of j, which again is just n of I of j divided by n, and then divided by the probability of C of I, which was the probability of how many data points were in cluster C over the total number of data points, and you multiply that by the number of data points in tau divided by the total number of data points. And so that gives you the entropy of tau minus the joint or the conditional entropy of tau given C is held constant. Yeah, so is there any questions on that? A lot of this is all repetitive information. We went over in information theory the basic concepts of what mutual information is, cross entropy, entropy, and these are the applications of those things, right? So, did I cut out?
No,
No.
you're
Oh, okay. I saw Nosa not moving, so I was like, wait.
good.
Okay. So, yeah, independence again. So you know that the probability of C will not impact the probability of tau. So the information of the joint, there's no information shared between the joint distributions, right? I mean,
Yeah.
that
Because
makes
they're
sense.
independent, yeah.
Yeah, they're independent, so they don't know anything about each other, or there's no correlation between either of them. Yeah, so mutual information again. We measure the dependency between the observed joint probability P of I of j of C and T and the expected joint probability PC of I times PT of j under the dependence assumption. Okay.
Hmm.
You could have a normalized mutual information. It's the geometric mean. I'm not exactly sure why you would normalize your mutual information, other than it might just be less data to store. But this is how you would do it. Take the information of the joint C and T, and then take the square root of uh, the product of the entropy of C and T.
Okay.
Does that make sense?
Yeah, I think you want to get, because the goodness of mutual information is actually dependent on the individual entropies of C and T. So
Right.
you normalize it so you have a more objective view of the mutual information as opposed to it being referenced to one particular entropy.
Yeah, that does make sense. Okay, cool. So pairwise measures. So this is a different approach to measuring how good your system is, and this is using the individual data points. So here they've got, so here they define true positives. Xi and Xj belong to the same partition T, and they are also in the same cluster C. So true positive pairs is saying that your true positives are your blue, or actually, I don't know why he aimed it blue, but I would say it would be like orange, your cluster one. So if Xi and Xj are data points within cluster one and ground truth one, it's saying that Y of I is, so they're in the same partition and in the same cluster. That's a true positive. Your cluster labels it as positive, and your ground truth label had it labeled as positive. So your prediction and your ground truth label match. That's what that's saying, for it to be considered as a true positive.
Partition is true, cluster is your model. Okay.
Yes. False and negatives. So your system says that your clusters are incorrectly labeled, but it should be, your ground truth labels say that it should be labeled the same. So this is a case of false negatives. And so that would be your false negative values. These are 2 points where they, like the orange right here described. You have orange in cluster one and orange in cluster two, but they belong to the same ground truth partition. Does that make sense?
Um, so X and I belong to the same partition T.
Yeah, so
Oh,
same
okay.
partition. Partition is your ground truth label.
Yeah.
Yeah, so they're both orange dots, but they're not in the same cluster.
Okay, I see.
I guess the concept here, we're looking at evaluation of a cluster by comparing pairs.
Exactly.
And
Yeah.
being like, hey, truthfully, these are the same, but our model says they're not. This is a false
Yeah.
negative. Okay.
And so actually, like in a lot of machine learning, you'll end up calculating your prediction versus your actual, and then you'll do some sort of normalization, and then feedback that into your system inputs so that you update your weights. Then it will make better predictions over time. That's how back propagation works.
Why would you want to do these in pairs? Like, how does that give you? Does that give you more information or something?
Well, let me see. I think oh, you know what? I think the reason they do it in pairs is because of some stuff below. There's like some calculations, like different types of calculations that take in pairs to measure things. I think it's also more about like where you. I think pairs help you determine where boundaries are, like where your boundaries are between two concurrent clusters
I see. Yeah, that makes
or
sense.
adjacent clusters. So it gives it's much easier. You don't have to sample the whole data set as a result, right?
Mm-hmm.
So I don't have to look at all of my orange data point, or like all the data points in cluster one. I only need to look at the most adjacent, like the two data points that are most that are closest to the boundaries between two clusters, right?
Yeah.
Yeah, I see. So it's
So
computationally cheaper than maybe other methods.
yeah, false positive. So these are situations where you have two data points and you have declared them to be apart. They're not in different partitions, but so the ground truth label says they're both.
But they are in different partitions.
Yes, they're not in different partitions, but they are in the same cluster. So what that would mean is that you'd have if they're not in in different ground truth partitions, uh, they are not.
No, they
They do
are.
not belong to the same partition.
That's what I meant to say. Yeah, so they
Yeah.
don't belong to the same partition. So that's why they have the example where it's an orange data point and a blue data point. They belong to two different ground truth labels or partitions. However, they've been classified in C2, which is C2. So that's the same cluster. So this would be considered a false positive. Okay. Next, we've got true positives. So true negatives. True negatives are basically where you have where they don't belong to the same partition, ground truth partition, and they also do not belong to the same cluster. So this is where you predict something to be false, and it is actually false. So
It seems like your borders will be, or at least your cluster borders are going to be among pairs that are either false negatives or true negatives.
Yes.
yeah, it seems like these examples, prove that. But I think you would need a little more. I wouldn't hold on to that idea for sure. I don't know if that plays out to be the truth in all scenarios, but in these examples, it is playing out this way. Okay, so pairwise measures. So here you're figuring out like true positive and then false negatives, false positives, and true negatives, and that is the sum of the event space, all ends, all positive outcomes. So we look at this. If we look at this bar graph or Venn diagram, I mean, bar graph. Yeah. So if you look at this Venn diagram, you see the whole event space of true negatives, and then you have false positives and you have false negatives, and then the overlap is the true. So true is your statistically least likely, or your smallest event space.
I see.
Yeah, so we can look at the math. Let's see. So because there are n equals n of n, this is permutations, right? N choose two.
Yeah, I guess so.
Which is n and then n minus 1 over 2 pairs of points. So we have the following identity. So true positive is described as the double sum, the 1/2 times the double sum of n of I squared j minus n. I'm not actually sure how they've calculated these numbers or like how they
Yeah.
derived these.
It
But
might just come from the permutation thing.
yeah, so I think. Oh, so you can see how they calculate true negative. This makes the most sense.
Well, yeah.
But
After you get all the other numbers.
the other numbers, yeah, not so much. And oh, okay. So false negatives are taking your so m of j represents
The number of points in that partition, in partition J.
yeah. So you're doing like 25 choose 2 minus true positive. So this is saying that false negatives would be like all the pairs of points, uh, all the pairs of points that were in in a specific partition J minus the ones that were told to be true. So that would mean that everything left there would be a false negative, right?
Mhm.
And then false positive is the opposite idea. So you're taking all the data points in a cluster, and then you're subtracting out the true positive. So that would say that, if something is true, or I guess you have all your data points and then you have the things that are true. So what you're left is with what has been labeled as false positives. Actually, I'm not even sure if that's the case. That might not have made sense. I'll look into this more and then try and send some updates.
Okay. Yeah, I mean, I think it makes sense intuitively, but I think you sort of look at the math a little bit to think about it. And
Yeah.
so.
Pairwise measures. So these are just four different types or three different types of statistical measures, right? They all do different things and they both work. They all work. Like, I think you just have to know when when to use these things, and that's just about it. So Jacquard coefficient measures a fraction of the true positive point pairs, but after ignoring the true positive or the true negative. So you take true positive divided by true positive plus false negative plus false positive. And so if you get a perfect clustering, it's equal to 1. The RAND statistic is a fraction of true positives and true negatives over all point pairs. So this is like accuracy. So I guess the RAND statistic is like scenarios where uh, false positives and true negatives. So this is like accuracy, right? It's like your system tells you when things are true and it's right, and then when things are wrong and it's actually wrong. So it does a very good job at telling you how accurate your system is. That makes sense. And then the Falk's Mallow measure. So that is the overall pairwise precision and pairwise recall. So we're calculating precision and we calculate recall and we apply the geometric mean to it. So this is very similar to doing that harmonic mean
Mm-hmm.
that we did earlier for the F-score measure that was defined, I think, up here.
Mm-hmm.
Oh, we might have to go way up. Oh, it's like way up. Okay, this one. Yeah, so it's effectively doing this, the F measure, right? Yeah, so this all makes sense.
Can you scroll up a little bit more?
Yeah.
Okay, thank you.
At least from my limited experience, I haven't heard of anyone needing to use any of these measures. Usually, like if depending on your use case, you'll use the F-score measure. You'll calculate the F-score for your clustering algorithms,
Mm-hmm.
uh, or you look specifically for accuracy. So you'll see you'll see the things I've seen the most in use has been specifically F-scores, accuracy, recall, and precision numbers, and not so much any of these like additional ones.
Okay.
Yeah. So we'll talk about internal measures for clustering evaluation. So this is when you don't actually know, you don't have a ground truth label or a data set to create, or a data set of partitions of ground truths. So here you're doing like the pairwise distance matrix. So you're calculating W between any 2 point sets, S and R, which is the sum of W, I, and J. So this is the sum of intra-cluster and inter-cluster weights. So the distance of a point is measured as two times, and then the weight, which I think is intra. This is intra-cluster. So it's basically calculating distances, like what the distances are like between any 2 points within your data point a cluster, and then you're also calculating the distance between data points between clusters. So that's what they mean by intercluster and intra-cluster. I haven't really, I don't actually know a lot about unsupervised learning and the ways that they use these sorts of like calculations to be able to produce predictions. So I don't have a lot of information. The beta CV measure, again, it's just another measure. You're basically calculating the ratio of the mean of intra-cluster distances to the mean intercluster distances. So you're basically normalizing, you're figuring out a ratio between how related data points are with it, like distance-wise within a cluster versus those same data points to other clusters. So it's like input, it's like input and then output normalized. Let's see. So the smaller the beta CV ratio, the better the clustering. And I guess that makes sense, right? That would mean that like your data points are tighter together. And it would also mean that your data points that are tighter together are further away from other data points clusters. Normalized cut. Yeah, it's just all a bunch of.
So beta CV, a ratio basically of how, or a measure of how tightly packed the clusters are together.
Yes. Related to how far away they are from other clusters.
Ratio. Okay. Yes. Okay. But it doesn't really tell you anything about like how well your clustering is.
Well, I mean, it would, right? The beta CV is effectively telling you that your data points.
Well, I guess I didn't complete the sentence. How well your clustering is with respect to some ground truth or something.
Right, because you don't have them. You don't actually have a ground truth. So there's a lot of times where you have unsupervised data or like a unstructured data. This is very useful in unstructured data sets. And what that means is like medical data tends to be very unstructured. So there are like, doctors' handwritten notes. There's like you'll take like a bunch of measurements about a set of patients that a doctor may see in a day or something like that. But they never tell you outcomes of like what the diseases are or any stuff like that, right? So if you wanted to produce like if you wanted to figure out the relatedness between the types of patients that a doctor sees per day and their ailments, you could use something like this to see how tightly can I cluster certain types of people, and then maybe I can make an inference about like their race or socioeconomic class or like something like that based on their health. Right. Something that you don't have a ground truth label for, because people would have to tell you what their income is or what their whatever it is, and the doctor has no access to that stuff. So that's beta measure. Normalized cut, it's about volume. So it's saying that the volume of CI is equal to the weight of the same not weight, but no, it is weight. So the weight of the cluster, comma the joint of the cluster and the volume. Does that make sense?
Yo, honestly, that's just I've reached.
I've seen this used, so I don't really know a lot. But I could give updates. So if I can find some additional reading material and then pass it on.
I mean, there's just a bunch of different types. It might just, for me at this point, maybe it's because I have a time crunch, but it might be a little more useful just to get the conclusion or just like a very vague overview of the rest.
Yeah, that's fine. So silhouette coefficient just tells you like the relatedness between, or I guess just like relatedness between clusters. All of these coefficients effectively are just calculating distances between the data points within a cluster and the data points going out to other clusters in order for you to tell like how good of a cluster is it. This Davies-Bouldin index is just talking about like specifically dispersion and spread of points. So this has to do with a lot, like this is variance or like the square root of variance. It's standard deviations. And so it's calculating the Davies-Bouldin measure for a pair of clusters C and CJ, or Ci and Cj, is the ratio of their standard deviations. And then you take the max, or you pick the max.
Wait, what's delta? Delta? Oh, it's the distance between the points and their means. Okay, but the delta is between the means. The distance between the means. Okay, so the variance of the clusters the sum of the variance of the clusters divided by the distance between their means, the center of the clusters.
Yes.
Okay.
Okay, so yeah, we did go super fast over the clustering evaluation or the internal measures.
But that's fine. It's just, they're just like you just plug in the numbers.
Pretty much, right. Yeah. So the more important part is that when you do the homework or we go through the homeworks, there are times where you'll need to refer back, and just knowing you can go look it up and then plug in the numbers.
Okay.
Yep. That's this week's lecture. So
Very, very well done.